So now I'll introduce the first inferential statistical test that we'll talk about in this class. It's called a z-test because it uses a z-score as part of its calculation. And for all these inferential tests that we talk about in this class, you'll have to figure out what the situation is when you would use that test. So the z-test isn't used very often in real research, but it's the easiest one to understand for like how the test works, and that's why we'll talk about it in this class. And really for this class, it'll be like kind of a foundation that we'll use to build upon to understand the other tests. And even though, like I said, you don't use the z-test very often, you could use it in real research, and you would do so when you have an outcome variable, a dependent variable, that's scale, so that means it would be interval or ratio scale of measure. The population mean is known, and the population standard deviation is known, right? Or you could think of these as given. So like in a class like this, I'll tell you the population mean or the population standard deviation. Or if you were really doing research, you would know these from some source like previous research, or maybe like like if you want to know the income, right? The IRS measures everybody's income, so that would be the average would be a known population parameter. And so the example we'll be working with for the z-test is the research hypothesis is that male students, this is men, SUU men are taller than American men generally. And the reason I'm using this example is the population mean and standard deviation of American men is known. And for all of these inferential tests, we'll be having our null hypothesis where you write H sub 0 sub naught colon. So these null hypotheses are about populations, and here the population mean of SUU is the same as the population mean of American men. They have the exact same height if the null hypothesis is true. And in all of these research, in all of these inferential tests, we're hoping that the null hypothesis is wrong. We're hoping our data will show something that's different than this. And in this case, we're hoping to show that given our data, it's more likely that SUU men are taller than American men. We're hoping that this is not the case, but we use these null hypotheses in order to do the math that's required for all these inferential tests. So now I'll explain the steps that you go through for the z-test, and I'm going to break the z-test into different steps that I'll also use for subsequent inferential tests when I explain them. And we're going to use the example research hypothesis that SUU men are taller than American men. And we can do that only because we know American men on average are 70 inches tall, and the standard deviation of American men is 4 inches. If we didn't have this information already, we wouldn't be able to do a z-test. And notice what we're going to do is we're going to measure a group of SUU men, and we're going to compare their measured height with the known population height to try to figure out if our sample is the kind of sample you expect from regular American men. So I'm going to go through different steps here. And the first step for these tests is going to be to identify what the null hypothesis is. So H sub naught colon. And the null hypothesis is the dull hypothesis. This is going to say that there's no difference. There's nothing interesting going on. So that would be the population height of SUU men is the same as the population height of American men. The second step will be to draw the population distribution. So I have these distributions already set up here. And these are all going to be histograms, frequency distributions. And this is going to be the population distribution up at the top, and that'll be true for the whole semester. This is the population distribution. This is of American men. Right? And these are individual men. And we're going to assume that this is normally shaped. The shape is a normal distribution. And this is going to be the population where we get our sample if the null hypothesis is true. We're hoping to find that our sample is unlikely to have come from here. Right? So this is the population distribution if the null hypothesis is true. So what we can do is, that's enough for us to tell what the mean is. The mean is going to be 70. So that's the mean of American men, 70 inches. The standard deviation is known, 4 inches. Okay, we know the shape, the mean, and the standard deviation of our population distribution if the null hypothesis is true. Next, we'll draw the sampling distribution, right? So that's going to be down here. And so it's going to end up looking something like this. It'll also be a normal shape. And remember, there's the 3 different characteristics that we'll need to know for our sampling distribution. We'll need to know the mean. So this is the mean of the sample means, the standard deviation of the sample means, and we need to know the shape. And recall from the previous video that the mean of this distribution is the mean of this distribution. So it's going to be 70 inches also. But remember, what the standard deviation is going to be shrunk in. And remember, the reason is what we're going to do to create this is we'll have to know our sample size. And in this case, we're going to go with a sample size of 100. So our observed sample is 100. We measured 100 SUU men, right? And so what we want to do with this z-test is we're going to calculate the mean of these SUU students, and we're going to figure out, is that the kind of sample mean that you expect due to random sampling from the population? And we're hoping it's not. We're hoping to have an unlikely sample, an extreme sample. Right? So with a sample size of 100 that we observe, what we're going to do to create the sampling distribution, and this is a sampling distribution of expected sample means. Sample means, just like we'll have a sample mean down here. And this is the expected sample means if the null hypothesis is true, because these are the sample means that you expect from this population. And it's due to random sampling. Right, so what I mean by random sampling is what we'll do conceptually. You don't actually do this yourself, but how this is created is you take a sample of 100 people at random from American men's heights. You calculate that sample's mean, and that goes down here, right? So that's one sample. You do that again for a different sample of 100. You calculate that sample's mean. You put that down here. You do that again for a third sample of different 100 people. Always 100 people. Calculated sample mean and put that down here. So you do that over and over for all possible, infinite number of samples, for all possible samples. You create every sample mean for all samples of 100 from this population, and this is the frequency of those sample means. All right, so these are this is the exact distribution of sample means that you expect from here if all samples are equally likely. And that's what random sampling is, when all samples are equally likely. So this is random sampling that connects the sampling distribution to the population. Right? And because these sample means have less variability, they're pulled in towards the middle compared to the population, you're going to have the standard deviation of this distribution, remember it's also known as the standard error, is going to be the population standard deviation divided by the square root of your sample size. So that's pretty easy to calculate. This is one of those formulas you'll just have to learn. So we have 4 divided by the square root of 100, so that's going to be 10. 4 divided by 10 0.4. 0.4 is our standard error. And the shape of this distribution will be a normal distribution because this one is. But even if the population's not perfectly normal, remember that the central limit theorem tells us that if our sample size is big enough, the sampling distribution will be pretty much normal anyways. And a sample size of 100 is plenty big enough for that. The fourth step will be to draw the observed sample distribution. And we'll do that on the bottom. And again, I'll be drawing it on the bottom all throughout this whole class. So we have the observed sample histogram here. And like the population, these are individual men. Remember, and this does not in any way depend on the null hypothesis. These are both completely determined based on the null hypothesis alone. You don't actually even need to observe any people to do these top two. This bottom part is what you actually observe in your sample. This is what the data that you collect goes down here. This stuff you'll never see. This is the stuff that SPSS or whatever computer program you use, this is what that computer program is doing behind the scenes. This is under the hood of the statistics program. Down here is the only thing you actually ever observe in your own research. And we'll say this 100 people, let's see, 100 people, and say their mean is 71.2. and the standard deviation is 4.2. So their mean is going to be over a little bit, and we'll just draw it. We'll just say it looks something like that. We don't actually have real observed data here, but the mean is 71.2, so it's right around there. For the fifth step, I will say that it's to identify the critical region, or we could also say the critical values of the test statistic. So for this, I first want to explain a little bit more about the logic of this test. So if the null hypothesis is true, which we're hoping it's not, then SUU men are just as tall as American men. The population mean height of SUU students is 70, just like it is for American men. And so what we did here is we drew the distribution of American men, and then we determined what kind of sample means you expect if the null hypothesis is true due to random sampling. And we want to figure out what's the probability that due to random sampling from this population, you'd get a sample mean of 71.2. Is this a common sample from the population of American men, or is it a really unlikely sample, in which case our sample is probably from a different population, which is what we're hoping, right? We're hoping our SU men are taller than American men. And because, remember, this is a normal distribution, and we already know that with a normal distribution, if you calculate the z-score of different locations on that normal distribution, you can calculate what percent is beyond it on any side. And that's how we can determine the probability that you'd get a sample as extreme or more extreme than the one that's observed. And so ultimately the approach is to figure out if this is a likely or unlikely sample to have come randomly from the population of American men, the null hypothesis population. And if it's a really unlikely sample, we're going to decide that SU men are taller. But on the other hand, if it's the kind of sample you would expect from this population, then we're not going to decide they're from a taller population. The decision about how unlikely it has to be is based on an agreed upon criteria. And that's called alpha. And alpha is 0.05, or you could also say 5%. And what this means is that of all the different sample means that you'd expect, if the null hypothesis is true, right, this is all if the null hypothesis is true, if your sample is so extreme, so unlikely that it only occurs 5% of the time, or 0.05 out of 1, this is the proportion version, if it's so unlikely it only occurs 1 out of 20 times, we're going to reject the null hypothesis. We're going to decide our sample is not from this population because it was so unlikely, and that instead it was from a different population. And so what we can do is on this normal distribution, we could color in this 5%, or equivalently this 0.05. And we're going to do so with what's called a two-tailed test. And what I mean by that is this distribution has a tail over here where it gets small, and we're going to do this test on both tails. All right, so we're interested in extreme sample means on this direction or this direction, really tall men or really short men. So we're going to have our 5% and we're going to split it across the two tails. So I'm going to color in that area. So what I'm trying to color in here is 2.5% of the distribution on this side and 2.5% of the distribution on this side. And that's the critical region that I just colored in. That's the critical region. It's critical in the sense that if our sample mean is in that critical region, and remember this distribution goes on forever because it's a normal distribution and it doesn't have any endpoint. If our sample mean falls in that critical region, we're going to decide to reject the null hypothesis, and then we're going to interpret our results as our sample is from a population of taller men, or if we're over here, of shorter men. So that's our critical region. Now what we can do, now that we've determined that we want 2.5% on each side, we can determine the cutoff z-scores. The z-scores, where if our sample mean is a z-score more extreme than that, then our sample mean's in the critical region, and we'll reject the null hypothesis. And those z-scores that have 2.5% beyond them on each side, those are plus or minus 1.96. When you're working with a sampling distribution, these z-scores take on special names. And for a z-test, this z-score is renamed a z-statistic. So these are the cutoffs, plus 1.96 and negative 1.96. These are z-statistics that are z-score on this is a z distribution because it's normally shaped. And that's actually, this distribution having a normal shape is why it's called the z-test. For example, we'll talk about t-tests pretty soon. And for t-tests, they have a t distribution and it's not normally shaped, right? It's only the z distribution only the z-test has the z distribution down here. Okay, so the z-score on this distribution is called a z-statistic. Remember, z-score is generally, it's the location of a score on a distribution, how far the score is away from the mean, in the numbers of standard deviation units. Right, so what we need to do is modify our z-score formula to fit this distribution. Right, so we're interested in the location of our sample mean, and the mean of this distribution is mu sub x bar, and its standard deviation is sigma sub x bar. So that's how I came up with the formula for the z-statistic, because I just took the z-score formula and I just made it fit this scenario where we're trying to figure out where our sample mean is on this distribution. Because we want to figure out if it's more extreme than plus 1.96 or negative 1.96, in which case it'd be really unlikely from this population, and we'd reject the null hypothesis because it's such an unlikely sample from here. So we have our z-score, those cutoffs, and these cutoffs have a special name. They're a special kind of z-statistic that are called the z-critical values. So the z-statistic values get this formula. These z-criticals are a kind of z-statistic. And the z-critical values are the z-statistics right at the edge of the critical region, where if you have a more extreme score on either side, you're going to reject the null hypothesis. So we have our critical region identified, it's drawn in. Over here I'll write the Z critical values are plus or minus 1.96. The next step will be to calculate the test statistic. And all of these inferential tests that we'll talk about will have test statistics and critical values. And for all of them, we'll compare our test statistic with our critical value. And if our test statistic is more extreme, in this case, if our z-score or z-statistic is more extreme than our critical values, we'll reject the null hypothesis. Right, so the test statistic for a z-test is called a z-statistic. Right, and this z-statistic is the z-score of our observed sample mean on this distribution of expected sample means, if the null hypothesis is true. When we talk about a t-test, the test statistic there is a t-statistic. When we talk about an ANOVA, another kind of inferential test, the test statistic there is called an f-statistic. Correlations have a test statistic called r. So all these different tests have a different kind of test statistic. For a z-test, it's called a z-statistic. Right? And I showed you how to make the formula earlier, so we're interested in the z-score of our sample mean on this distribution. So we want to know the location of our sample mean on this distribution. So we'll just plug our values in here. So our z-statistic is going to be 71.2. That's the sample mean minus the mean of this distribution, 70, divided by the standard deviation of this distribution. So this is going to be 1.2 divided by 0.43. Our z-statistic is 3. I'll write that down over here. So this tells us 71.2, this observed sample mean, is 3 standard deviations over to the right, because it's positive, on this distribution. Right? So here was about 2 standard deviations, so we need to go over 1 more. So our observed sample mean is actually, we now know its location. It's 3 standard deviations over. So it's actually about right there. So remember I colored in the critical regions, which is here and beyond. So our observed sample mean is going to be in the critical region, and ultimately we'll end up rejecting the null hypothesis because of that. And we're going to decide, because this is such an unlikely sample to have come from this population due to random sampling, that our sample in fact came from a population of taller men. The 7th step is to decide either to reject the null hypothesis and decide that it's wrong. That's one option. Or option B is to fail to reject the null hypothesis. Notice we do not have an option here to accept the null hypothesis. So to reject the null hypothesis means to decide that this is false. Means to decide about the populations out in the world, the SU men are not the same height as American men, right? And so to make this decision, what we're going to do is we're going to compare our z-statistic with our critical values. Right, they're 1.96, negative 1.96. Those are our critical values. I'll put that here, 1 plus or minus 1.96. We're going to compare those with our z-statistic of 3. In this case, it's 3. And if our z-statistic is more extreme than our critical values, we reject the null hypothesis. And generally, it doesn't matter if you're talking about positive or negative, so I'm actually going to put these in here as absolute values, because in practice, that's the way you end up doing it. So that means that if our z-statistic, if our z-score is greater than 1.96, that's our critical value. So if this is the case, then you reject the null hypothesis. In the current situation, 3 is more extreme than 1.96, so we are going to decide to reject the null hypothesis. That means that we're going to decide that in the world, SUU men are taller than American men, and we're going to say taller because 71 is greater than 70. Notice we could be wrong. We could be making an incorrect decision because the kind of samples that you expect from this population, if the null hypothesis is true, it's actually, remember this distribution goes on forever, and so this kind of sample, it does show up every now and then from this population due to random sampling. Not very often at all, right? That's a very, very unlikely kind of sample, but it's plausible. It does happen. Maybe like 1 in 1,000 times or 1 in 1,000,000 times, right? So we could have a very unusual sample just due to random sampling. But it's so unlikely that we're just going to follow the rule of if it happens less than 5% of the time, we reject the null hypothesis. So in this case, we rejected the null hypothesis, but I want to talk about another scenario. Let's just say for a second that our z statistic was 1. That means that our sample mean was only 1 standard deviation away from the mean here. Would have been at 70.4. So if our sample mean would have been 70.4, our sample mean would have been here, and our z statistic would not have been more extreme than our z critical, and in this case we would have failed to reject the null hypothesis, because the null hypothesis is a pretty plausible explanation for why we would have got a sample like that. That would have been just the kind of sample. Remember the sample mean there would have been 70.4. 70.4 is the kind of sample mean that you expect to get from this population due to random sampling with sample sizes of 100. It's pretty common. So we don't have enough evidence to reject the null hypothesis. You don't do anything like accept the null hypothesis. Accept the null hypothesis. So you don't conclude the null hypothesis is true. You don't conclude that, in fact, SUU men's height is exactly the same as American men's height. And you don't do that because for a sample mean that's right here, this is a population where this is a plausible kind of sample that you would get. But this is also a sample that is very likely to have come from a different population if the mean is 70.1. That's another population that fits the sample really well, or 70.2, or 70.3. In fact, there's an infinite number of different population means, or populations up here, that would produce a sample just like that, depending on how specific you want to be. So 70.323, 3, 4, 5, 6. That could actually be the real population that produced this mean. This could be the actual population mean, right up here, that could produce the observed sample. So that's why you can't accept the null hypothesis, is that, in fact, whatever your sample is, it's consistent with lots of different populations up here. It's not very good evidence that it's from this exact population that was specified under your null hypothesis. So for step 7, you either decide to reject the null hypothesis if your test statistic is more extreme than your critical values, or if it's not more extreme, you fail to reject the null hypothesis. The 8th step will be to interpret your findings. What did you learn from doing your study and doing the statistical analysis on your data? Remember, this is the only data that we had. This is the only observed data that we had down here, right? But knowing this about the population, in this case, we were able to decide that our sample was really an uncommon kind of sample from this population, and so we rejected the hypothesis, the null hypothesis, that SUU men are the same height as American men, that SUU men's height is 70, right? Because that's mathematically equivalent. So now what do we make of our findings? And it's pretty simple here, don't overthink it, right? So we decided that our observed sample is not the kind of sample you get from this population, and our observed sample is over here, taller. It's higher. It's of taller men than American men. So our interpretation is just going to be that SUU men the population mean of SUU men is going to be greater than 70. SUU men are taller than American men. So this is the kind of findings that we were hoping to get with our research hypothesis in the first place, which was the idea that SUU men are taller than American men. If our sample would have been shorter than American men, if it would have been 69 or maybe 68 inches, if we would have rejected the null hypothesis on the other side, if we would have rejected the null hypothesis and our sample were on the other side here, then our interpretation would be that SUU men are shorter than American men. So even though our hypothesis, our research hypothesis, was hoping to find that SUU men are taller, if our data end up showing that, boy were we wrong. Not only are they not the same or taller, they appear to be shorter. They appear to be a sample that came from a population of shorter men. So that's how you'd end up interpreting these findings with significant results. But let's say we got a z statistic of 1, like we were talking about a little bit ago. There we would have had to fail to reject the null hypothesis. We didn't have enough evidence to suggest this was wrong. And there the interpretation is that the findings, the study, the results are inconclusive. You've done all of this research and you don't know if your population of interest of SUU men are taller than American men, shorter than American men, the same height as American men. When you fail to reject the null hypothesis, the result is a completely inconclusive study that didn't really tell you much of anything beyond what you started with. And so that means when you're doing a research study, you want to be really careful to try to set up your study in advance. So if there really is a difference in American men and SUU men, that you're going to be able to reject the null hypothesis. And setting up a study really well so it's able to do that is called having a high statistical power. And we'll talk about that later on. So here our finding interpretation was that SUU men are taller than American men. All right, and there's actually one more step that I'm going to include here. I'm going to call it step 9, but really it's kind of part of interpreting the findings. And I'm going to call this calculating the effect size. There's more than one way to calculate effect sizes. And one of them is just to determine how much taller we would guess SUU men are compared to American men. How many inches taller? So our best guess of SUU men's mu, of their population mean, our best guess, now that we've decided it's not 70, our best guess is that it's the same as our sample mean. Right, so we're going to use our sample mean to estimate our population parameter. So our sample mean was 71.2, so we're going to guess that's what the mean of SUU student men's heights are. It's our best guess. We don't have any more information that would give us a better guess. So given this, we can, with this assumption, with this parameter estimate, we can calculate what we think the difference is. So we could take the height of American men and the height of SUU men. These are our best guesses at the population parameters. And if we do this, we would get 1.2 inches. So our best guess is that SUU male students are 1.2 inches taller than American men. And this kind of an effect size, just in the, I'll call it the raw units, inches are the raw units for this data, this is pretty interpretable. And so if this is actually what study you're doing, this would be a good kind of effect size that would help you interpret your results. So not only can you interpret these findings as SUU men are taller, but they're taller by 1 0.2 inches. In most research, the raw units is not an informative kind of effect size. And so there's a more standardized approach to these effect sizes that I'll talk about. And it's called Cohen's D. So Cohen's the guy's name, Jacob Cohen, and he created this effect size called D. And Cohen's D is another z-score. Right, we've got z-scores all over in this class. And this is the z-score. Remember, a z-score is a score on a distribution, and so it's the number of standard deviations the score is away from the mean. And Cohen's D is a z-score up here at this level. And Cohen's D tells us how many standard deviations away the observed sample mean, that location on this distribution, how far away it is from the population mean. So we can plug all these values in here, right? So Cohen's D, the formula is the sample mean minus wherever our sample mean is up here, minus the population mean divided by the standard deviation. So we can calculate D now. Cohen's D, 71.2 minus 70 divided by the population standard deviation of 4. 1.2 divided by 4. So Cohen's D in this case is 0.3. That tells us, given our best guess of what SUU men's height is, as our parameter estimate for SUU men's heights, we go over 1/3 of a standard deviation. Right? This is where 71.2 is. 71.2. Right, this is SUU men's heights. Our best guess is SUU men's population mean is 1/3 of a standard deviation over. And if we wanted to, now, we could draw what we think it's like. It's actually, this is our best guess for SUU men. And Cohen also provided some guidance for how to interpret these effect sizes. I'll talk more about it later, but for now, I'll just give you the overview. Right, so for Cohen's D, we're going to have small, medium, and large effect sizes. And those are going to correspond to Cohen's D values of plus or minus 0.2, plus or minus 0.5, plus or minus 0.8. And these are just kind of rough benchmarks, right? So in this case, we got a 0.3, which is pretty much a small effect size. You could maybe argue small to medium, the small to medium effect size. And the nice thing about a Cohen's D effect size is that you could use this for heights. You could use it for like a 1 to 10 scale of happiness, where a 1 and a 3 aren't interpretable numbers, but a Cohen's D of 0.3 tells us that they're at the population level, the populations are about 1/3 of a standard deviation apart. And so Cohen's D are nice because they're a standardized effect size unit that can be used whenever you're comparing two different means, like we are here for SUU men's heights and American men's heights.